The following is a brief review of optical MEMS. This video includes an overview of optical MEMS, different types, fabrication mechanisms, applications, and a few concluding remarks.
So the early work on optical MEMS applications was inspired by sensors and actuators developed in suspended films. Optics and photonics are among these research fields impacted by MEMS techniques. The ability to steer or direct light is one of the key requirements in optical MEMS. So optical MEMS is the fusion of three technologies: micro-optics, micromechanics, and microelectronics. The advantages of combining these technologies is that photons have zero mass, therefore only a small force is required to operate these devices, and the devices can be mass-produced at a lower cost because of its reduction in size and weight. The following are several different types of optical MEMS. Communications can include fiber switches and tunable optical devices. Data storage, detectors, displays can include projections and virtual reality, adaptive optics, micromirrors, and switches.
Surface micromachining is an additive process in the fabrication of optical MEMS that is achieved by thin film deposition. Layers of structural and sacrificial materials are alternated to produce the desired design. These images show this layer deposition and removal process. Bulk micromachining, as shown in the figure to the right, is a process in which substrate materials are removed to create 3D structures through wet or dry etching. Three types of etching are potassium oxide, ethylene diamine pyrocatechol, or reactive ion etching. Deep reactive ion etching allows etching of anisotropic, randomly shaped, and located features into a single crystal silicon wafer. This process only uses photoresists as an etch mask. Inductively coupled plasma Botch process allows for near vertical etching in silicon. This process is also used in grayscale technology. Surface micromachining, bulk micromachining, and deep reactive ion etching are only a few types of fabrication mechanisms for optical MEMS.
In telecommunications, one application is mechanical actuation. Here, the input channel guide is fabricated on a cantilever suspended over an edge cavity. Surface electrodes deflect the cantilever from side to side electrostatically to allow connection to one of the two output waveguides. Switching times are of the order of milliseconds. Another application is 3D imaging. Structured light can be projected onto the measured object using a scanning microsystem that employs a single-axis torsional MEMS mirror that steers a near-infrared laser beam on a diffractive silicone microstructure, which shows a deformation of the projected line that are then detected with the CMOS camera. From the line deformation, object depth and size are determined. A third application is a miniature methane sensor. This uses a low-cost near-infrared broadband light source with a micro-ring resonator that acts as a cone filter to match the methane absorption lines as many as possible. Light and methane interact with each other in the gas phase chemical sensing area, and the absorbed light is monitored by transmission resonant peaks of the micro-ring filter. The wavelengths can be adjusted to detect other gases. Some challenges include sensing, controllability, and reliability of the optical MEMS devices. Future trends include all optical network and 3D imaging in outer space.